So our keynote speaker on battery innovation is Dr. Esther S.Takeuchi, who is a SUNY distinguished professor in the departments of material science and engineering and chemistry at Stony Brook University. She also has a joint appointment at Brookhaven National Lab as chief scientist. Prior to her academic appointment, she was employed at Great Batch Incorporated, where her achievements in lithium battery research, particularly on cells for implantable applications, led to a number of key technological developments, including the lithium-silver vanadium oxide battery, which powers the majority of implantable cardiac defibrillators. A prolific inventor, she holds over 150 patents. Dr. Takeuchi is a member of the National Academy of Engineering and has received numerous awards for her research achievements. In 2009, Dr. Takeuchi was awarded the National Medal of Technology and Innovation by President Obama. In May 2011, she was inducted into the National Inventors Hall of Fame. She was elected as a charter member of the National Academy of Innovation in 2013. She also received the E.V. Murphy Award and a Stellus Award from the American Chemical Society and the Electrochemical Society Battery Division Technology Award. She is a fellow of the Electrochemical Society and the American Institute of Medical and Biological Engineering. Dr. Takeuchi received a bachelor's degree from the University of Pennsylvania with a double major in chemistry and history and completed a PhD in chemistry at The Ohio State University. She completed postdoctoral research at the University of North Carolina and University at Buffalo. Her research focus is novel power sources, including development of new materials and investigation of ferratic and non-ferratic mechanisms relevant to battery systems. Please join me in welcoming Dr. Esther Takeuchi.
Thank you so much for the introduction. It's such a pleasure to be here and be considered as part of this eminent community. It really is an exciting time, I think, for innovators. So in putting together this talk, I started to think about what really is innovation. And so we think about innovation being an idea, but I think ultimately it comes down to taking that idea and translating it into something that matters, something that people care about, and something that makes a difference. And I'd like to share with you actually one of my favorite quotes about innovation and discovery, and that is that seeing what everybody has seen and thinking what nobody has thought. So it's not so much about new data, although it can be. It really is about ideas. When we're looking at things, what is the idea that sparks our minds and get us moving to turn that idea into a concept and a functional device? So innovation crosses many, many different fields. And over the course of these days, we're going to hear about many types of applications. But of course, I need to talk about the application and the device that I know best, which is batteries. And so at the university, I teach a class actually on electrochemistry and energy storage. And sometimes the students ask me, what's so hard about this? Batteries have been around for a very long time. How come we haven't invented the ultimate battery yet? And part of that answer to that question is that there are so many different applications and so many different needs, and depending upon what the application is, the nature of the power source really does need to be very different. So in a satellite, for example, you would want a battery that was very, very lightweight. Batteries are actually used to power devices that recover oil or help in oil exploration. And in those type of applications, high temperature survival and surviving high shock and vibration matters. And I'll touch, in a moment further about batteries for the grid and for electric vehicles. But, as my introduction said, much of what ties this together in my experience really is developing batteries for implantable medical devices. So I think of it as a battery is really tethered to an application, and we think about the successful applications and successful batteries, they're really linked very closely together. Oftentimes batteries can enable a device, but by the same token, without that device, the battery is really not necessary. But as the technology changes, the batteries also need to change to keep pace with the evolution of technology. So let me give you a couple examples. You know, lead-acid batteries have been around for many, many, many decades, but yet the vast majority of us still have them in our cars today. Why? It's because they fill that need better than anything else. They're effective, they're inexpensive. These days, they're recycled. So in spite of the fact that they're lead, they're actually fairly environmentally benign because of the recycling. Lithium iodine batteries power pacemakers. Lithium iodine batteries don't do anything else very well. They're extremely sensitive to temperature variation. They can only deliver very low levels of power, but for a pacemaker, they can go on for years and do that job remarkably well. An interesting story is lithium ion. So lithium ion are the batteries that power virtually all of our portable electronic devices. You know, these days, phones, computers, iPads, iWatches, all these things that are coming along. And that battery was really pioneered by Stony, not by a battery company, but an electronics company who said, we need a better solution for our devices. So if we want to sell our devices, we need a battery that can effectively power them. So today, some of the bigger challenges really are electric vehicles and batteries that help back up the grid or help enable renewable forms of energy generation, which are often intermittent. And what the end game will be there, I think, is still open. You know, there are many things that are under exploration, but the final solution, I think, is being tested right now. So the story I want to tell you a little bit about is the battery for the implantable cardiac defibrillator. You know, when I look back on it, it was really a stroke of good fortune for me that one of my very first projects ended up being a very important one. But I can tell you at the time, it was actually daunting. You know, we were facing a challenge with a device that was just being demonstrated as effective with a battery that was not suitable. The battery that they were using for the demonstration only lasted about a year. And what we wanted to do was develop a battery that lasted 5 years. This is not rechargeable. So this is 5 years functioning in a device without being recharged. The battery had to be really small because the whole device is small. It's put inside of people. And one of the biggest challenges was that the batteries that were used in implantable medical devices in fairly reasonable numbers were the iodine batteries that I talked about for pacemakers. So one day I sat down and translated, the pulse power of a pacemaker, which just sends a little tiny electrical shock to remind the heart to beat, compared to a defibrillator, which has to interrupt these large-scale arrhythmias for the heart. And the difference in power was 1,000,000 times. So how do you develop a small battery that can last 5 years, that can have 1,000,000 times more pulse power to help defibrillate the heart? And at that time, that battery, that could do all of these things really didn't exist. So it did all start with chemistry and materials, figuring out, what are we going to make as the anode? What are we going to make as the cathode? How are they going to communicate effectively with an electrolyte? And we did end up, after considering and actually trying several different components, with lithium as the anode and silver vanadium oxide as the cathode. And I do want to highlight this picture, actually. My husband teaches honors freshman chemistry. And much to my surprise and delight, a few years ago, the book that was selected for freshman chemistry was a book by Martin Silberberg, and I flipped back to the electrochemistry chapter, and lo and behold, the SVO battery was the battery that he put in freshman chemistry. So I thought, wow, that's pretty great. The freshmen today are learning about the work that we did on these batteries. So let me talk about invention and reinvention. So the original battery, when we first came up with this idea and said, okay, we think we've got something that's going to work, 2 patents. And over the course of several years, well over 100 patents, reinventing this battery. Virtually every aspect of it, modifying the anode, the electrolyte, the cathode, and how the battery was actually designed and assembled from a mechanical perspective. And these are just some of the patents that covered some of those aspects. And in the end, the battery ended up being very successful, but more importantly, it enabled the widespread use of the implantable cardiac defibrillator for people who have a tendency to cardiac arrhythmia. These devices really are life-saving, and the statistics in clinical trials comparing people with ICDs to without them and their life expectancy are really, really dramatic. So there's no doubt that this is an effective form of human therapy that has saved, over years, millions of lives. These days, there's about 300,000 implants per year. I wanted to talk about the role of intellectual property. Now, in this context, it was actually in a small business, but I think that being very strategic, particularly in a small business, intellectual property still plays or can play a remarkable role. With small business, we all know, patents are fairly expensive, so you've got to be very astute in which patents you decide to file and which patents you push forward. It may not be possible to push forward all of them. So I think what was important for us as a small company at the time was that we recognized how important these patents could be, and we thought about not only where are we today, but where does the device, where does the battery need to be in the future, and work towards what we anticipated in terms of changes and cover that ground with intellectual property. So if you tether the invention to an application, whether it's battery or otherwise, that can be hugely important. Patent inventions broadly with respect to application, and as I mentioned, the future needs of an application. And even though the company was small, it effectively, for decades, was able to compete against much, much larger, multi-billion-dollar organizations with larger investment, R&D investment opportunities because, I think, of the intellectual property portfolio that we're able to assemble over those years. So what does it mean to introduce a successful battery? I could tell you over the history of time, there aren't that many different battery technologies that have been successful, and that's why this is a pretty significant event. From a humanitarian point of view, it did enable the widespread use of the ICD. The company growth and sales from the battery were really significant. This ended up being a very not only profitable but growth area. And it was one of the factors that facilitated the transition of the company from being a small business to being listed on the New York Stock Exchange. And for me, I was very fortunate that the work that we did was broadly recognized. And at the time, while I knew the product was important, the level of impact that it had in the day-to-day was not as apparent as it became later. So if I had to provide advice, I think that the key is understanding the application and the interaction of the battery and the application, because it's really the application that determines what the battery needs to do. It also is important to be able to understand how the battery functions, not just in a chemical sense, but to be able to interrogate it wisely in terms of what it can do when it's actually deployed. It's funny, in many fields, there are metrics that are established. Oh, well, we have to hit this number, we have to hit that number. And sometimes those metrics are extremely useful because they drive towards a goal. But sometimes those metrics can also be limiting because you perhaps prematurely discount directions and technologies that might end up being promising for the entire panoply of characteristics that they provide. And I think being able to successfully meld scientific as well as engineering concepts is critically important in the ultimate deployment and execution of a device like this. So I wanted to touch for a few moments on some of the things that we're doing right now in terms of battery science. We're worried about developing batteries with higher power. So power, if you remember, is watts. It's current times voltage. And batteries have a limit of voltage by thermodynamics. They're typically voltages of someplace between 1 and 4. But current can change by orders and orders of magnitude. So that's what we're trying to do, is increase power through increasing current. We're looking at multifunctional materials, and I'll have some examples of these. Batteries that are made with earth-abundant, environmentally friendly materials, and also, as I mentioned earlier, large-scale batteries, perhaps integrated with cars or the grid. We've found and been able to demonstrate that the properties of the material, in terms of the physical properties and the defects, dramatically influence electrochemistry. So through solid-state synthesis and synthetic techniques, actually using low-temperature approaches, we're able to change the physical properties of the materials where we can double the electrochemical output. So we're not changing the amount of material in a battery, we're changing how the battery material works when it's in the battery. So pretty dramatic impact through material design and manipulation. One of the things that energy storage folks sometimes don't want to admit, so this is a big secret in this bar chart here, is if you look at the amount of active material in the battery versus everything else, so packaging, all of the inert components, the amount of active material actually can be pretty small. So what we're looking at is what I call multifunctional materials, so materials that can play more than one role. Oftentimes, you'll have an active material, it'll be surrounded by carbon, some kind of a polymer in order to make a functioning electrode. But we've developed materials that grow their own conductive network. And by growing their own conductive network, not only is the network more effective because it grows where it needs to be, but we can eliminate some of the inert components in the battery and start moving these bars closer together. I also want to talk about lifetime of batteries. Lifetime and lifetime prediction remains a remarkable challenge for energy storage. But the key really is understanding why they fail. Batteries typically don't fail because they run out of active material. Something else goes wrong. And this actually is a story of following up in academics on the SVO battery that I studied so many years in industry. One of the things that we discovered was that if you try to extend the battery lifetime of the ICD battery, let's say from 5 years to 10 years, the failure mode is actually very low level solubility of the active material in the electrolyte. So I challenged actually an outstanding graduate student of ours to take this on as a challenge. And what he's able to demonstrate was that not only could he measure and develop the methodology to measure low levels of solubility of inorganic materials in organic liquids, he was able to do it quantitatively, and he was able to do it in a way where we could actually establish kinetic relationships. Once we had these kinetic relationships, and this is the first time this has ever been done, now we have a way to actually be predictive. We can understand how much material is going to dissolve over time and then use that as a predictor to begin to predict lifetime based on this failure mode. Further, we were able to take batteries that did not work very well anymore, these blue ones down here due to solubility, compare them that did work very well, do detailed analysis of the anode surfaces using a technique called micro X-ray fluorescence at Brookhaven Lab using a synchrotron, and actually develop a conceptual model of why the solubility of the cathode and the deposition on the anode was causing such a problem in terms of battery function. And in some cases, you get a functioning battery, and in other cases, the battery simply doesn't work anymore. This experiment and these series of experiments actually are particularly gratifying for me. For many years working in batteries, the way you figure out what happened was you test the battery to a certain point, you take it apart, take the pieces out, analyze them, and hope you can reconstruct the story. X-ray radiation at synchrotrons now is powerful enough, it can be tuned finely enough through slits to be able to, on a micron scale, actually penetrate the can, the stainless steel can of a working battery, and probe what's going on as the battery is activated or as the battery is discharging. So what we did in this case is we actually had batteries encased in, oops, wrong button, in stainless steel housings. And we placed them in the beam of the synchrotron and then slowly move the battery through the beam. So we're able to collect actually 56 diffraction patterns through the thickness of the battery. We can measure these diffraction patterns in various locations of the batteries. And what's so significant about this is now we can track where the reaction is taking place. Not only what is the reaction, but where is it happening. So we can create 3D maps of the reactivity of these battery cathodes and find out what's the limiting mechanism. And much to our surprise, many times the limiting mechanism, which oftentimes has been assumed as access to ions, wasn't the limiting mechanism, but oftentimes the access to electrons was actually the limiting mechanism. So it's electronic conductivity that was slowing down some of these reactions. So with this information, we can redesign the battery, both in terms of materials and three-dimensional construct, to further improve the power capability of the battery that without these insights gained with this three-dimensional mapping would not have been possible. So what's going on now? The challenges are really, I think, the big challenges are twofold. Their power and their lifetime. So if I speak about power first, when we think about portable devices, we measure the power more in watts or maybe low tens of watts to power these devices. But as we're moving to backing up, the households, backing up the grid, running cars, we're talking about many orders of magnitude increase in power. It's about 100,000 times power differential. And if we think about lifetime, portable devices today are really designed about a 3 to 5 year lifetime. It's about the lifetime of a cell phone contract, right? Nobody would imagine these days keeping the same cell phone and getting a new battery, ditch the whole thing, get a new one. So there hasn't been much of a push to increase lifetime because in the marketplace it would be meaningless. But as now we're thinking about moving to electric vehicles, and now I'm talking about fully battery-powered vehicles, the battery really should last the life of a car. They're too expensive to replace. So maybe 10 years. And when I start talking to people who are involved in the grid and large-scale power generation, they think in multiple decades, 20 years plus. So we have a lifetime challenge of moving advanced functioning batteries from 3 years to 10 years to 20 years. And so our strategy really is to go back to the concepts that we used in my lab looking at batteries for medical devices, where we had to move from pacemaker batteries to ICD batteries, increase power by 1 million times. We've been thinking about batteries lasting 5 to 10 years in human implants for a long time. So while the batteries are not the same, the technology is not the same, the concepts and the approaches towards investigations and thinking about how to increase power and lifetime are very strongly based on the work that I was able to do with medical devices. So I want to close with a couple quotes. This is a quote from Sam Rubin. The reason I chose Sam Rubin in particular is that way back when pacemakers were first invented, they were actually based on mercury batteries, again, that lasted maybe a year and a half. And that's what was available at the time. And Sam Rubin was the inventor of the batteries that were originally used for the first pacemaker. And he says, progress has always required creative thinking and a determined effort in the pursuit of bold dreams, however imaginative. Goals become reality only when ideas are complemented by working technology. And I think that captures really the notion of innovation, that we have an idea, we want to push the idea forward, we think the idea is going to be great, but ultimately it's got to work. We have to demonstrate it, and it has to do something, whatever its intended function is, it has to do that successfully. The last thing I wanted to close with was some thoughts about perspective. You know, innovation really is about ideas, and I think many times if we can get a diversity of perspectives, those ideas really appear to be very creative because they're coming from a different perspective than everybody has looked at a problem before. So if people from a single perspective are trying to solve a problem, oftentimes you bring in somebody with a different perspective, you seem to get very different ideas, but really they're just looking at the problem from a different way. So when we think about innovation and think about solving problems, I encourage us to involve not only multidisciplinary thought processes, which I think are really critical to innovation, and I see that in my research group all the time as we bring together people who are physicists, chemists, material scientists, electrical engineers. They think about problems in a different way, but also different types of people, I think, approach problems with different perspectives and can bring new levels of creativity and innovation to the problems at hand. And lastly, I just want to sincerely congratulate the class of 2014 on their induction into the National Academy of Innovation. This is a wonderful organization that promotes the idea of innovation, promotes the idea of invention. I think it's really taking hold in academic environments, and I'm thrilled to be part of it. Thank you very much. So I've been encouraged to answer questions if there are any. Question is about fuel cells. So that's actually a great question. Fuel cells, in terms of the energy content, are very high, and they're appealing from that perspective because the energy content can in fact be much higher than a battery. So the challenges with fuel cells are that the power delivery, so the ability to give that jolt of energy fast, is pretty difficult. So I think they're definitely going to play a role. I think for, especially in applications where the immediate need for power is not so high, but maybe you just need kind of sustained delivery for a longer period of time, they can be highly successful. Maybe some kind of hybrid of multiple technologies will end up being the ultimate solution. I know for electric vehicles, they're looking at fuel cells in conjunction with looking at batteries, so we'll see who wins in the end. Yeah?
I was wondering if you could, son? I was wondering if you could tell us what you think is the sort of furthest out potential technology for batteries right now. The one that you think is perhaps the most exciting, but the most distant from application.
So if I look at just energy content, the highest energy content in a battery that I'm aware of is a battery called lithium air. So lithium is extraordinarily lightweight as an anode. So it's going to be really hard to beat lithium. And of course, the appeal of something like an air battery is that the cathode essentially goes away. You know, you get a cathode for free. So just for energy content, lithium air is out there as kind of the, you know, the ultimate victory. Having said that, I do think that it's a number of years away from successful implementation. You know, there's still research going on, but pretty daunting challenges still in front of it.
There's been a lot of activity in getting anodes into nanostructured materials, reducing the size. What do you see as the future and the advantages in that?
No question. Nanostructuring is playing a key role. And part of what we're doing synthetically is actually we're making nanomaterials synthetically directly. Historically, so you know, going back in time, many battery materials were, you know, I would say micron sized, and then the pathway forward would just put everything together and mill it. But anybody who works in the world of nanomaterials knows that you can't really mill to the level that you want. So I really think that the low temperature synthetic approaches where we can directly control material properties through nano-sizing, morphology control, and even three-dimensionality really make a difference in how effectively the batteries function. Okay.
It's all right. Do you think that since you could analyze inside of a battery, will you be able to repair one?
Whoa, that's a good question. Interestingly, people are looking at that, particularly with batteries that are called flow batteries. Flow batteries have the electrodes and then some kind of liquid goes between them, and then that liquid ends up, you know, sometimes being the electroactive material. And what's being investigated is, can you flow something through there for a short period of time? Let's say the battery has to work over many years, but then you have a way to, you know, rebuild the battery quickly. And I think that's showing some promise. You know, whether we'll be able to do it without any external let's say any external intervention, so without any external materials being introduced, possibly that's more difficult to envision, but certainly by temporarily introducing some kind of additional material or new material or flowing away some kind of passivation layer, I think that's going to happen. I think, you know, there are things that are close today.
Thank you very much.
Just one more thing. I just wanted to, this is not a question, I know it was the last question, but I was sitting here, you know, 'cause we've been on a committee before and I never heard you talk and it was wonderful, but one thing I was thinking, I don't know if people knew, is, you know, the man with the most patents is Thomas Edison on electricity and DC current, and the woman with the most patents is working on electricity and batteries, so very interesting. Thank you so much.
You know, Paul, I just have to follow that up with a very short comment. When I received my 50th patent, Mr. Greatbatch, who was the founder of the company where I worked, wrote me a letter, and I have it framed in my office. He said, you know, congratulations on your 50th patent. You know, you're still far behind Thomas Edison. He has whatever it was, 1,000 something or other. He said, but you have a big advantage over him. You're still alive. So.